Next up, we have Alan McConnachie of NRC Herzberg to tell us about the next new instrument at Gemini, GHOST, which we look forward to getting assembled, installed, and commissioned on Gemini South as soon as the current pandemic conditions allow. So Alan, I see you're sharing your slides. If you would turn on your video and unmute yourself, please go ahead. Thank you. Oh wait, now we're back to a preview of your slides rather than the display mode.
Yes, I had to switch my mute off. Can you hear me all?
Yes, I can hear you and I see your title slide now. Perfect.
Fantastic.
Thank you.
Thanks very much. So we very much hope that this will be one of the next go-to workhorse instruments for the Gemini observatories. We are all very proud of it, the group who have worked on this now for several years, many of whom are in the audience today, I see. GHOST, the Gemini High Resolution Optical SpecTrograph, is a next generation fiber-fed high-res optical spectrograph for Gemini. It's a collaboration between the Gemini observatories, of course, teams in Australia, particularly at AAO and the ANU, and here also in Victoria at NRC, the Herzberg Research Centre. Now, Michael Ireland is the project scientist for this. I'm also on the science team and sort of the project scientist for the spectrograph part of the spectrograph. The Australians, in particular AAO, have been working on the fiber feed and the CAS unit. The software is done by ANU, and the instruments spectrograph system is done here in Victoria. Now, you're all aware of the sort of science that can be done, and indeed GHOST has grown out of a long-term need in the Gemini community for this capability. There were white papers submitted quite some time ago now, which sort of stimulated all of the requirements for it. But I think this also highlights really the challenge that the instrument team have taken on, and I think really done very well with, which is we are a latecomer to a well-developed field. There are lots of high-resolution spectrographs on 8-meter class telescopes. Keck High-Res, ESO has some great spectrographs, Magellan, Mike, and many others. And so therefore, given that, we don't just want to be another one out of, a collection. We want to be the best. We want to be the go-to high-resolution spectrograph for the entirety of the astronomical community, all of the Gemini partnership, and frankly, we hope everybody wants to collaborate with the Gemini partnership in order to be able to use this instrument. And so in terms of what the requirements have translated to, in terms of what you're going to get at the telescope, this is a high-resolution spectrograph where the entirety of the optical wavelength, from slightly blueward of 360 nanometers out to beyond 1 micron, is available in a single shot. There's no need for multiple setups. It's not a narrow wavelength range. You get the entirety of the optical spectrum at once. Indeed, at low resolution, or we'll call it standard resolution, because that's R55,000, you can do it with 2 objects simultaneously and about a 7 arc-minute field of regard. You can also go to even higher resolution, close to R of 90,000, and observe a single target at that resolution, again across the entirety of the optical wavelength range in 1 shot. This is a highly stable instrument. I'll go into some details about how we make sure that it's going to be very easily calibratable over both short and long-term timescales. And while we haven't explicitly designed this to, enable the measurement of precision radio velocities, and by that I mean meters per second, a HARP-style spectrograph, we do believe that over the years we will be able to push down towards those sorts of numbers. And this is going to be, I think, a really fascinating and really interesting science-enabling capability for the observatories. As you'll see at the end as well, this has all been done with the thought that we are going to be observing lots of very faint targets. So we have very high throughput and a very good observing efficiency. You're not going to be wasting lots of time acquiring a target and things like this. We can make all these claims because while we are late to the field, we've also therefore been able to benefit from increases in technology that have happened over the past decade, indeed, which have happened during the design and fabrication of GHOST. So, for example, the 6x6K detectors, which allow us to get the entirety of the spectrum on just a blue and a red detector. The fact that we can actually do that is because we can now have these large format, high quantum efficiency coatings, which were not available a decade ago. This couldn't be done. UV enhanced silver coatings, the sort of throughput, the losses on each reflection now are very, very small. And again, we have a lot of very good blue efficiency for Gemini, even within various reflections, and even though the UV is so hard to do well. As you'll see, our enclosure and the entire setup of this instrument is highly stable, temperature stable as well as vibrationally stable. And due to some really great innovations in the optical design led by John Pasder and colleagues here in Victoria, we've got some really nice features that really increase the image quality. For example, the field curvature of the cross disperser is essentially non-existent. This means you have fantastic image quality. Again, I'll show you what that means in practice. The cross dispersers that we're using are fantastic. They were, I suppose, perhaps one of the last that Kaiser Optics has produced. As for those of you who know about the SpecTrograph world, Kaiser Optics has decided to not do astronomical DPH gratings anymore, which is a massive loss to astronomy. But we have some fantastic gratings that they've helped develop for us. The camera designs are very nice. One of the things for those of you who are used to looking at shell spectra, you will notice a very nice feature in the spectra that I show you towards the end of this talk, which basically just makes the data format much easier, hopefully makes the data reduction much more intuitive and practical as well. And the optical mechanics is likewise very nice. The concept is this: it's a fiber-fed instrument. So you have the CAS unit, where you have the IFUs. These go down approximately, I think it's about 30-meter fiber cable down to the QD room, where the NOIRLab, sorry, where we have the whole bench SpecTrograph system. At the telescope, we have two IFUs. The first IFU is the two black hexagons that you see, as well as the smaller one. And then at the bottom, you have a second IFU. You'll notice there's a bunch of different fiber configurations there. So what you have here is you have two standard resolution IFUs, both about sort of 1 arc second, just under 1 arc second projected onto the sky, as well as some sky fibers. These can be positioned to target two different objects. Or you can do that mode, or you can use the other mode, which is the high resolution IFU bundle with, on the other set of IFUs, you have the high resolution sky fibers that go with it. Now, what happens is that these miniature IFUs, the slit is reformatted through the fibers to produce two different slits. And so on the left, you see the slits corresponding to the standard resolution mode. On the right, you see the slits corresponding to the high resolution mode, where you see in the standard resolution mode, you have the two black object fibers, and in between them, you have some sky fibers. And for the high resolution mode, you have the high resolution object fibers, you have some sky fibers, and you also have a simultaneous calibration fiber where you can send down a thorium argon lamp as well in order to sort of really do some very nice wavelength calibrations. The actual SpecTrograph that this gets fed to, we describe as a box in an isothermal box. So this was the CAD rendering of it in the NOIRLab in Gemini, and inside the ghost enclosure is another enclosure surrounding the bench. That outer enclosure is fantastically temperature stable. It uses these very nice NTC thermistors in such a way that the heat is evenly distributed around the entirety of that outer box. That inner box itself, that bench is vibrationally isolated, is incredibly stable. What this means, and in fact, this is what it looks like assembled in Victoria. What this actually means is as the ambient temperature outside, and this is just was outside in Victoria, where the temperature is not the most stable, you'll see, despite those large variations, the actual variation spread by multiple temperature sensors distributed throughout that box, there is no variation. It's incredibly stable down to the levels of almost millikelvins. It's really a very, very nice system. The optical design, again, there's been some really nice improvements in the design here that we are the first, I think, to actually implement, in particular the white people relay design, with the result that 80% of the energy actually gets concentrated in a single pixel. So a single pixel is about 15 by 15 microns, and we're able to put sort of 80% of the energy that goes down the fiber into one of those pixels. It's really quite remarkable. And again, all of these are very high efficiency optics. Again, I'll show you what this looks like in practice. This is the design, but of course, reality is what matters. The optical mechanical design, again, is a very stable, vibrationally isolated system. And again, you can see it actually as it was constructed in Victoria. Detectors, for those of you who are used to looking at detector QE curves, you'll notice that for both the blue and the red CCD there, these are incredibly high efficiency. So the actual delivered efficiency is the yellow dots. And you can see you're above 90% wavelength efficiency, everywhere except the extreme red and the extreme blue. This is really nice detectors. You can in fact see I'm sure he's smiling under that mask, the face of Greg Burley, who was really one of our go-to detector peoples. And this was before masks were the thing to wear. But this was when we were putting things together. And again, it's just some really, really nice components that we're able to use here. And the first slide used a very, very high quality piece of paper in the lab back in 2019. We had this assembled. And there's John Pazda, who has been sort of one of the lead engineers and the lead optical designer for all of this. I believe he's on the call today as well, showing the first spectrum that we got through GHOST. We fully assembled everything in the lab at Victoria, and we were able to do a lot of tests in the lab. So all of these are real data. This is the blue and the red CCD images of what happens when you put a mercury lamp down GHOST. And so this allows you to see the spectral format, where because of the limited number of mercury lines, we were also able to sort of see exactly what wavelengths we get. The free spectral range is indicated by the diamonds on the left and right of each shell. You will notice the different orders. There's a lot of overlap. So for the blues go from 63 up to 96. And the red goes from 35 up to 65. So again, there's 3 orders of overlap there as well. We can also confirm that we have spectral coverage from 359 nanometers out to just slightly beyond 1 micron. Again, very broad wavelength coverage. So I mean, there's a tremendous amount of data here anytime you get a GHOST spectrum. Trying to advance my slide, and it's not. So just 1 second. One moment, and my computer has frozen. I'm not sure why. There we go. The delivered image quality is fantastic. What we did here was we used a tiny fiber, a 10 micron fiber. Recall that the pixels of GHOST are 15 microns. That means essentially all of the light should be concentrated in a single pixel if we've done things correct. And when we zoom in and then put things on a logarithmic or square root scaling here, you'll notice that, yeah, actually more or less all of the light is concentrated in just a single pixel. And so this is, again, remarkably nice image quality. And it really will mean that we can get this very, very nice data format, very, very efficient SpecTrograph. Such that, in fact, when you actually look at a full slit, this is the red detector where we've zoomed in on some slits here. You can actually see that, recall that this single slit is in fact multiple fibers, and you can actually see the individual fibers that make up the slit in each of these. But further, those of you who are used to looking at shell spectra, you'll be aware that the shell orders are slightly curved, and as they're curved, the slit ordinarily tilts and changes its tilt as you move across the detector, as you move across each order. That's not the case here. John was able to come up with some incredibly clever techniques which completely cancel out. So the curvature is introduced, the tilting of the slit is introduced at various points in the design. And he's actually done it such that they all sort of cancel each other out, such that the slit basically stays aligned with the CCD columns from left through to right. Again, making the data format just that bit easier to understand and to interact with from the sort of science use perspective. Ironically, GHOST has no ghosts. We did our best to burn a hole in the detectors by putting a very, very bright lamp down the fibers. And this is what you get, some really nice illuminated slits, but you'll notice there's almost no ghosts. And in fact, the only ghost that a few of you might see down at the very bottom of the red is in fact outside of the wavelength range that we were supposed to design for anyway. So who cares? Bottom line of this is, again, this will help us push down to those very faint limits, push down to those really faint signatures. And so this is going to be a very nice thing indeed. Empirical measurement of the spectral resolution means that we're getting to a resolution of about 55,000, and we're critically sampled everywhere in the standard resolution mode, similarly in the high resolution mode. And just, I see Henry's reappeared there. So just very briefly, this is the signal noise of the observation of a star, about the 10th magnitude star, but it just shows the relative throughput of GRACES, high-res, UVES. What we were designing for, the requirement was the solid line, the solid red line. What we were designing for was the red dash line. In the end, what we've actually measured, and again, this is through empirical measurements in Victoria, is the gray line in this plot. The gray line is the actual throughput. This is involved with combined with the Gemini telescopes. So you will see we are significantly better throughput than high-res, UVES, GRACES as well. GRACES is great in the red, but GHOST is great everywhere. So this is going to be really, I think, very nice. We shipped it in February 2020. It was making its way down the coast of the Americas. Everything was great. Then there was a global pandemic, which was not actually on our risk register. We will put our hands up to that. So most of the major components are currently sitting at Gemini. We still have the very precious optical components here ready to ship by air just as soon as we are able to figure out how to travel down there. We can't wait to do it. I think everybody's very keen to get this on the telescope. We think it's a fantastic instrument. We have some fantastic a science program as well. One of the things that the science team is able to do a science program where all of the data is going to be available to the entire community, because essentially troubleshooting the entire system, because obviously there's going to be a few hiccups as we put something on the telescope. So we have a science program which we hope to run over the first several semesters of GHOST, where we want to be looking at very faint stars in the galaxy surrounding the Milky Way. Stellar chemistry will be a key part of GHOST. Also, Michael Ireland will start investigating this instrument for actual planetary observations. It should be fantastic. Please, any questions you have for me now, I'm happy to answer them. I will also be doing one of these chat sessions later on, so please feel free to join me then. Thank you.
Thank you, Alan. That was excellent. And yes, it's somewhat scarring seeing those containers again. I'm glad we at least have the instrument on the summit now safely, and we look forward to getting it on the telescope. Let's see. We do have a few questions here. What is that just went past me? What is the setup time for each object and sky configuration?
Very short. I can't recall, but it's measured in a few minutes. I don't recall the exact number, perhaps one of the others online will, but no, it's very short. And I should also note as well, a lot of that setup time, a lot of it's usually spent acquiring objects as well. And the IFU has already been commissioned, actually. It was able to be commissioned independently of the bench SpecTrograph. So we already know that which can be one of the biggest time sinks for observations, we already know that works very well as well. So it should be very efficient.
Excellent. Let's see, another one is the data reduction pipeline ready?
The data reduction pipeline works perfectly with our simulated data, which is to say, of course, there's going to be some iterations on it. This is work with the ANU and Michael Ireland in particular. I hope you lead that. That's going to be one of the major things that both the science team, the commissioning team at the telescope, and also the Gemini Observatory will be working on during and immediately after the commissioning. So we think we have a good pipeline. But again, integrating it once you actually get confronted with real data, because even when we make our data imperfect, we make it imperfect in perfect ways, right? So that's just reality. So we have every reason to believe that we should have a good version of the pipeline very soon after we start getting the first data from GHOST, and that will, of course, be part, I believe, of the whole Dragons environment. And in fact, I'm sure we'll be learning about that very, very shortly.
Great, thank you, Alan. Given the time, we need to move on. There are a couple more questions in the chat that perhaps you could try to answer offline after the session, and people can continue to ask questions in that chat after the session. So thank you again, Alan.